By applying the definition of the derivative, we want to show that the derivative of x square with respect to x is equal to 2x. So let's try to show that. But before that, we need to know what is even the definition of the derivative, right? So how can we apply that then to find the derivative of x square is 2x. So do you know what is the definition of the derivative? If you have f of x is a function, and then the derivative of that with respect to x can be figured out by applying this definition, which is find the difference cosine of the function. So find what is f of x plus h minus f of x, and everything underneath that is divided by underneath that is h, right? And then take a limit on this difference cosine. That means we need to see where this difference cosine approaches when h gets to 0. So that is the definition of the derivative. We want to use that to show that the derivative of x square is 2x. So to do that, let's assume that the function itself is x square, and then we can show that its derivative is 2x. Okay, but to do that, we also need to find then what do we need to find first? According to this definition, we need to find the difference cosine. So we already know what is function. We need to know what is f of x plus h. So let's find that first. So how do you find f of x plus h from x square? Well, we just replace x by x plus h, right? So in that case, we'll have x square of x plus h. But what does that mean? If I need the expansion of these, I need to multiply x plus h with x plus h, right? And I can use the, what is the method? I can that method I can apply here to multiply these two FOIL, right? So we can apply multiply first term with first term, and then which is on this case what is x times x square, and then I can multiply the outside term. So x times h will be x times h, right? And then I can multiply the inside term, which is h times x will be, again I can say h times x or x times h, and then I can multiply the last term as h times h as h square, right? So that's what we have. And then if that is the case, then this is x square. We have the like term to combine here. X times h plus x times h will be 2 times x times h, right, plus h square. So this is the expansion of square of x plus h, right? So we can then apply that expansion over here to see what the difference cosine look like. So let's try to work on that. So let's first find the difference cosine. That means first find what is f of x plus h, which we already figured that out. So we just need to copy that. So what is that one? X square plus 2 times x times h plus h square, right? So this is our f of x plus h, and we have minus sign here, so we need to write that down. And then we have f of x, right? So which is we assume on this case is x square, so we can write it down over here, and then everything underneath that is it. So this is our difference quotient. If you want, we can actually simplify this. Let's first remove the parentheses. So on that case, we'll have x square plus 2xh plus h square, and then minus x square, right? And everything underneath that will be h. And what do you see here? We see the like term to combine, positive x square, negative x square. When we combine, we get 0, right? On that case, we have then 2xh plus h square over h. So this is our difference quotient. But to find the f prime of x, as we have said on the definition over here, we need to apply the limit there, right? So let's try to see where this function, this difference quotient approaches when h gets closer and closer to 0, and then that will give you the derivative. But let's try to apply the limit here. So when h gets to 0, we see that the denominator approaches to 0, and then you can see each term on the numerator also approaches to 0 because there is h involved over there. When that gets to 0, the whole quantity approaches to 0. On that case, the top or the numerator is getting closer and closer to 0. The denominator is also getting closer and closer to 0. So what do we have then? We say on that case we have actually 0 over 0 type of form, which is known as indeterminate form. So we have indeterminate form of type 0 over 0. So on that case, what do? we try to see if we can cancel out the zero common factor. Can we do that on this case? So if we just look into this expression over here, I see that the h can be taken out on the numerator. When we do that, we'll have 2x plus h, also the same common factor here on the denominator, and then I can immediately see that actually this h and h are a common factor right at the top and bottom, so we can actually cancel that out. So we just cancel the zero common factor because that was the quantity that makes this expression here at the top and then top and bottom. Because of that quantity it was zero, right? So we cancel that factor out. So if that is the case, then now what we just need to do is try to see if we can find the limit of the remaining expression. And so that means we just need to find the limit on 2x plus h, right? When h gets closer and closer to 0, we're going to see where this expression approaches. But as you can clearly see, when h gets closer and closer to 0, the first term is just 2x, which is independent of h, right? So there is no h term involved. So when h gets closer and closer to 0, 2x will be always 2x. So it doesn't depend on what happened with h. But the second term is actually when h gets closer and closer to 0, this will approach to 0, right? The second term will approach to 0. Sorry, on that case we can just say that the limit of this 2x plus h when h gets closer and closer to 0 is just 2x. Okay, so let's try to see if we prove that or not. Our original function was given here as x squared, right? So that was the given function, and then we apply the definition of the derivative, and then it turns out that the f prime, if f of x equal to x squared, f prime of x is actually equal to 2x, and then that's exactly we needed to prove, and we proved that result here by applying the definition of the derivative.